Yeah, the St. Louis Arch is sort of typical in that from there you could see the way the shape of the arch is, where the loads are concentrated. If you look at it, you'll see at the very top, the apex of it is sort of a thin section because there's not too much load being accumulated there other than just the weight of that particular section.
Built between 1963 and 1965, the 630-foot-high arch is a masterpiece of design. The legs of the arch are 54 feet wide on each axis at ground level and taper to only 17 feet at the top. The massive foundations that support it were dug 60 feet deep, 30 feet of which extend into bedrock. The giant arch is supported largely by the outer skin, which is composed of stainless steel weighing over 900 tons. The arch was stacked out of individual metal sections. Cranes lifted each new segment toward the top until the last keystone section was placed. While the gateway arch must support itself vertically, it must also be able to sustain high lateral forces, such as winds.
So we have to make sure we have a thicket anchored where the arches end.
This giant arched form was as much an artistic statement as an engineering landmark that drew on a classical shape.
I think people are drawn to arches really just because it's a familiar form, mostly. It's something that you've seen throughout history. Almost every period has an arch appearing, and it's so familiar to people, that's what makes it appealing.
The St. Louis Arch is perhaps the ultimate expression of the arch as art. But the basic shapes of arches, domes, and tubes continue to serve us in a stunning diversity of ways. Even submarines use the power of the arch to do their stealthy work.
Submarines are pressure vessels that have to resist the great force of the water, particularly when you go deep underwater. The internal pressure just wants to crush a submarine. And so the section of the hull, the shape of it, is a circular shape that resists this pressure in compression. So you can think of a submarine as a circular arch.
The U.S. Navy's newest submarines use this tried and true design to dive deeper and prowl farther than ever before. Modern submarines are completely cylindrical, which enables the entire structure to become an arch in compression. And they use more arches inside, in the form of braces, to withstand pressures of over 400 pounds per square inch as they dive to record depths. In addition to the cylindrical shape of the hull, each end is capped with a dome, further strengthening the vessel. Modern submarine hulls can be up to 3 inches thick, and many are able to dive below 2,000 feet. This is accomplished by augmenting the strength of the arch with exotic metal alloys. These metals must combine the ability to become compressed with a tendency to be elastic, so that the cylinder doesn't fail under the crushing pressure. So in effect, the arches used in a submarine must survive both compression and tension at the same time. These advanced technologies may lead to the colonization of Earth's final frontier, the bottom of the sea.
When we talk about extreme environments, one example would be under the water, where you have the structure acting as something that resists compression, because the water is very heavy and it creates enormous forces upon the habitat where people live. So in that case, they're acting as compressive structures, and they tend to be rather thick because they have to withstand the pressure.
But with modern alloys and composites, people should be able to live undersea without fear for years, even decades at a time. On dry land, the arch has been used for years in the design of semi-permanent battlefield structures, now used in civilian life, such as Quonset huts.
And all that was a big arch, elongated arch in one direction, and it was very efficient to put together very fast, and of course that military made great use of that.
The Quonset hut's strength is derived not just from the arched frames, but also from the multi-arched corrugated materials used to cover them. New designs continue to evolve, using this same time-tested shape. In another exciting application, the U.S. Army is experimenting with a giant inflatable arch, able to lift huge loads. These arches are also used inside giant inflatable buildings and may one day replace structures such as the traditional Quonset hut because of their increased portability and ease of construction. But the strength of the arch goes beyond the confines of Earth. For anywhere gravity applies, the arch will serve as a basic element of construction. On the cold, dry surface of Mars, arches, tubes, and domes may house the communities of the future.
The habitat, pressurized space, have the same laws of physics governing their design. And if we look at, for example, historic arches, they assume a certain shape because of the laws of physics. The same thing happens in space. They're the same laws of physics that govern operations in space, but the conditions are often different. And over my shoulder, we have a model of one of the Mars-based scenarios that we've established that has a variety of different kinds of elements.
Most planned lunar and Martian colonies utilize tubes and domes in their construction. Some are inflatable, while others are made of hard plastics, composites, and metal alloys.
We work with geometries. Our curved shapes are usually pressure vessels. So they tend to look like cylinders, thermos bottles, those kinds of things, but they typically are all circular in section.
But some of the most recent and daring plans for colonizing Mars harken back to the Roman era, using local materials for arch construction.
Because it takes 6 to 9 months to get there, you want to use local materials on Mars in order to build. Well, what materials are available on Mars? There's essentially rock and dirt. This project developed an entire settlement on Mars, essentially a small city, made only out of arches and domes. It almost looked like an Islamic city from the Middle Ages. But it's what we consider to be the most high-tech solution to the problem of building on Mars.
These structures would become, in effect, tunnels, and house these interplanetary explorers under the Martian surface. Similar structures already house astronauts in Earth orbit, and via deep space voyages, will someday reach even further into the solar system. Our building blocks in space, just as those that have served us on Earth for thousands of years, will utilize the properties of that most basic of shapes, the arch.